Hello again. In this video, we're going to continue with section 6.2 on exponential functions, page 95. And we're going to start with example 3. Example 3 asks the question, are the following functions exponential? So if we look at part A, the answer is yes. Because if you remember from our last video, an exponential function turned out to have a variable in the exponent. Right? We're multiplying by a factor of 3 each time. When t is 1, it's times 3. When t is 2, times 3 again. So that's the definition of exponential. So exponential functions always have a variable in the exponent. If you remember our linear functions, the exponent in the variable was 1. And then quadratics, the exponent in the variable was 2. And then we went to see what happened when the exponents were negative, fractional. Now we're looking at when the exponent is a variable. And they're in the form where q equals f of t equals a times b raised to the t. That's what we saw on the last page in the last video. So B is also a yes, where C is a no. Why is C a no? Because the variable is not in the exponent. So the question also asked if they are exponential, identify the initial value and the growth factor. So if you remember, A is the initial value and B is the growth factor, which I added on the right. So here, the initial value, the A, is going to be the 275, and the growth factor is going to be 3. In part B, the A is the 80, and the growth factor, which is the initial amount, and the growth factor is 1.05. So there's the initial amount, there's the growth factor. We don't have to do it to part C since C is not exponential. So go ahead, you guys try the same thing with exercise 1. You can pause it, come back. It says that the number of grams of algae in a pond after t days is given by this formula. How much algae is there initially? After 1 day, after 5 days, what does the 20 and the 2 tell you about the algae? By the way, this is exponential because it has a variable in the exponent. So go ahead and pause it if you have not done so already, and come back when you are done. Okay, so how much is there initially? So I'm going to let t be the number of days, and I'm just going to make a chart comparing t with our equation, our expression in this case. So initially means when it's 0, which we already know that it's the 20. You can see, if I plug in a 0, this would be 20 times 2 to the 0, and 2 to the 0 is 1, so it's indeed 20. What about after 1 day? The answer should be 40. Plugging in a 1 there. And plugging in a 5 after 5 days, what would that be? The correct answer should be 640. I can show you that one. That one I plug in a 20 times 2 to the 5. We always do the exponents first. Don't do the 40 first. So it would be 20 times 32, because 2 to the 5th is 32. Then if you multiply that on your calculator, you should get 640. What do the 20 and the 2 tell you about the algae? Well, we already know the 20 was the initial value. And we know that, we didn't write this down, but they said that the algae was in grams. So that tells us there are 20 grams of algae initially. So that's what the 20 tells us. The 2, what does the 2 tell us? The 2, if you remember, was the growth factor. So it tells us that 2 is the growth factor. Great. So let's try exercise 2. Same idea, but now instead of a 2, we have a 1/2 there. Again, you should pause it, but let me read it first. At some point, an aquatic herbicide is introduced to the pond, and the algae begins to clear. The number of grams of algae remaining t days after the introduction of the herbicide is this expression, 8,000 times 1/2 raised to the t. Fill in the table. So go ahead, fill in the table. And then then you can do part B. If the amount of algae was described by this expression, 1/5 instead of 1/2, what would be different? Go ahead, pause, try it, and then come back. Here's the solution for part A. Did you get it correct? This one now, since the factor is 1/2, it's going to decay. They call this a decay instead of a growth. And how much it's decaying here? Well, it starts at 8,000. You plug in 1, so 8,000. I'll just show that. 8,000 times 1/2 to the 1, so it would be 4,000. Plug in a 2, right? Half again. Plug in a 3, half again. You could do that for each case. 8,000. Just do it for one more. Oops, that's supposed to be 1/2. To the 3, that's like saying 8,000 times 1/8, which is indeed 1,000. So you can see that it does work. What is different if you had a 1/5? Well, let's look at that. I'll make a chart again. It still starts at 8,000. Now you plug in a 1, that would be 8,000 times 1/5 to the 1. So what is 8,000 to the 1/5? That is 1,600. Plugging a 2 in again, it's like we're going to be dividing by 5, right? 1/5 of that is 320. And again, to see that would be 8,000 times 1/5 squared would be 8,000 times 1/25. Hopefully, if you use your calculator, that is 320. You can see that it's going to decay way more rapidly. So the higher the number down here, the more it's going to decay, right? Because now we're going to divide by 5. And then this one we're going to only divide by 2. So we're going to see more about that in the next section. So let's do the next exercise. Go ahead and try this on your own. Model the situation. The number of animals in a population is initially 880, and the size of the population increases by a factor of 1.14 every year. Go ahead and try that one. Pause it. And come back when you're ready. Yes, using our formula, f of t equals a times b to the t, we know the a is the initial amount, so that's the 8, oops, there's a mistake, 880. And the size of the population increases by a factor, so that is the b. I can now call it the growth or decay factor, because what's part B? We'll call it Q, since that's what they called it here, and they don't have a variable for us. So Q is equal to the initial amount, which is 20,000. It decreases, so that means it's going to decay by 0.4 every day. So the B would be the 0.4, the factor, and the 20,000 would be the initial amount. We're going to see from our next page that this right here is a growth when the growth factor, or when the B is bigger than 1, because then we're multiplying. Even 1.14 gets a little bigger each time. But if this is a fraction, a proper fraction, less than 1, then this is going to be getting smaller and smaller and smaller, like the 1/2. So this will be a growth since b is bigger than 1. And this is going to be a decay since b is smaller than 1. You can turn the page and look at exercise 4 now before you start the next video and try the graphs of these functions to see what they look like when it's a decay versus a growth. And also the formula for this is on the next page as well.